Greetings, everyone. So we've been working in section 8.3, and we started 8.3 by learning the integral test. And then we learned some other tests along the way. And at the end of the section here, we're coming back to an idea of trying to approximate the value for a convergent series and trying to tell somebody how good that approximation is. And we call that bounding the error. So let's talk about that a little bit here. For the sum of a series, we have S, okay? That's what we typically call the sum of the series. If we want to approximate the sum of the series, we approximate by using a finite number of terms in the addition. So instead of adding up the infinite number of terms, we add up some finite amount. We add up, or we find the nth partial sum. The error in the nth partial sum, which is what R sub n represents, is just the difference between S and S sub n. And we use absolute value here because we don't really care about whether the difference is positive or negative. We just want to know how far away that distance is, or that approximation is from the actual value. So we want the distance the approximation is from the actual value. So this is our error, or our remainder. Now, in general, we're not going to know the value of the error or the remainder exactly, because if we did know that, then we can certainly just find S, okay? We do this in those cases where we don't know how to find S, or we can't find S, and so the best we can do is find an approximation. So we use S sub n as an approximation. R sub n then is something that we want to at least tell somebody an approximation to. Not really an approximation to, actually. We want to tell somebody what it's bounded by, what it's less than, so they have a sense of how good the approximation is. Now, in our notes, we gave a quick visual description of where this inequality comes from down here. R sub m is trapped between two integrals, two improper integrals. The improper integral from n plus 1 to infinity of f of x. Then f of x is the function that models the terms of the series at the values of integer values, and it's also bounded below or bounded above by the improper integral from n to infinity of f of x dx. So what this allows us to do is it allows us to tell somebody that our error is in this range here. It's our approximation is about this good. We'll talk about what we mean by this good in just a moment. So suppose we wanted to sum the series 1 over n squared from n equals 1 to infinity. This is kind of a famous one. Leonhard Euler worked on this back in the late 1700s, I believe, and was the first to come up with the exact value. So we know the exact value to this one, and it allows us to then look at an approximation and compare it to the actual value and have a sense of what's going on. So to approximate this, of course, we would only use a finite number of terms. So let's use the first 20 terms for the approximation. Something else we also did in class. My marker's having trouble here. That's supposed to say 20 of 1 over n squared. Now, if you run that through your calculator, and you got to know how to do that, you're going to get about 1.59616. Now, how good is that? Well, that's what the bounding of the error is for. So, to bound the error, since I use the first 20 terms, my n is 20, so the first integral starts at 21 and goes to infinity, 1 over x squared dx, less than or equal to r sub 20, which is less than or equal to the integral from 20 to infinity of 1 over x squared dx. Now, both of these improper integrals are things that you should be able to evaluate. So I'm not going to go through the mechanics of evaluating these improper integrals. I'm going to go right into their values because that's what we're focusing on at the moment. So the improper integral on the left works out to be 1 over 21, and the improper integral on the right works out to be 1 over 20. Not too hard to find those values. Now 1 over 21 is about 0.047619, And, whoops, r sub 20, this is going to be 0.05 over here. Now, what is this actually telling us? Well, looking at the value over here, when I notice this 0 over here, this is telling me that the actual value and the approximation may have the first digit the same, okay? In fact, they don't, but I'll talk about that more in just a moment. How do I know that? Remember, we said r sub 20 is going to be equal to the absolute value of s minus s sub n. Actually, in this case, s sub 20. So, well, what am I doing here? I'm subtracting two values, at least in theory, because I don't actually have it. I actually haven't done it yet, but I'm subtracting s and s sub 20. Well, when I subtract two numbers and I get a 0 someplace, that means they had the same digit in that place. And if I subtract something over here, it means I got another, and when I have another 0, it means I have the same digit in that place. Possibly. It does depend on what's happening with this third digit over here. That third digit, second after the decimal place, but that 5 that's right there, the problem with that digit is it's pretty large, and I might have had to borrow in order to do the subtraction that ended up giving a 5 in this spot right here. There's no way for me to tell that, but I can't assume I didn't borrow, so I have to keep that in the back of my mind. So I know the first digit I got was correct, so when I got the 1.59616, the 1 is good, the 1 is correct. The 5 that we got might be correct because there's a 0 right after the decimal point here. But I have to account for the fact that I might have had some borrowing to do to get this 5, which means that that digit might not be correct. And in fact, it's not. Okay? So what I want to see for an accurate number is my error bounded by something that has a lot of zeros over here. The more zeros it has between the decimal point and some non-zero number, the more accurate it is. The smaller the error bound, the more digits that the two numbers have in common. Okay? So, well, this is a mess that I was going to erase, so shouldn't have seen that. It means nothing, though, at the moment. So, what does this mean? So, if I'm giving you here what the series is equal to, or approximately equal to, with much more accuracy than the first 20 terms. I'm actually taking the actual expression and simplifying or expanding it to a decimal and writing it out like this. So these are trusted digits, is what I'm saying. Now, if I take this and I subtract from it the 1.59616 that we got earlier, so I can actually calculate what r sub n should be, and again, there's a little bit of a rounding error on the right-hand side here, but this is good enough. I get 0.0487708. I think I probably used a few more digits in the calculation, but I'm only showing you this. These are all done on paper on the side. But notice this, that the error that we got is smaller than that 0.05. This is less than, I can put the error equal to, 0.05 that we calculated the error should be bounded by. So it worked, okay? The integral test gave us an error that was smaller than, or that was bounded above by 0.05. On the other end, it was bounded by 0.047619, and this is bigger than that. So I can put the 0.047619 over here, less than or equal to, and then this value is in between those two. So obviously, the integral test worked. Okay, but we're going to need more than 20 terms to get a good, accurate approximation for this. So what if we ask this question? How many terms are needed to have the error bounded by 0.00005? So in other words, if whatever my application is into that I'm applying the math for this problem to, if I needed my number to be this good in application for whatever reason, how many terms would I have to add together to make it that good? Well, remember, before I say remember, what we're interpreting this to mean then, of course, is that we want R sub n, or what it's telling us is that R sub n has got to be less than or equal to 0.00005. Now we know that that R sub n is, that R sub n, that looks horrible, is less than or equal to the integral from n to infinity of f of x dx. So I got to figure out the n that makes, I got to figure out the first n that makes the improper integral from n equals from n to infinity of fx dx less than or equal to 0.00005. That's what we have to do. So, of course, we're doing this for the same series that we've been working on here. And so this is the improper integral from n to infinity of 1 over x squared dx. I need to get that less than or equal to 0.00005. And that too looks terrible right there. Well, if you work out this improper integral, it works out to be 1 over n. We saw when n was 20, it worked out to be 1 over 20. This works out to be 1 over n. You should be able to demonstrate that. So I need to figure out the value of n that makes 1 over n less than or equal to 0.00005. My pen is sticking to the screen right now, so it's not writing very well. Well, if I take reciprocals and I get n greater than or equal to 1 over 0.00005, we can work this out, and this is actually 20,000 over here. And so we would need 20,000 terms added together in order to get all the way down to 4 decimal places that are accurate. And it's actually 3 would be accurate. The 4th one might have a rounding error because of this 5, or a borrowing error because of this 5. So that's a lot of terms. That means this series is converging very, very slowly. And so, if you're going to display digits on a calculator or computer, you'd have to add together many thousands more than 20,000 terms to get an accurate answer in this way. So, very slow. Okay, so here's another example. We need to find the sum of the series, the sum from n equals 1 to infinity of 1 over n to the 6, correct to 4 decimal places. So what do we mean by this correct to 4 decimal places part? That's what we got to understand first before we can start working this out. So remember before when we were talking about the error, I need the error, which of course is the difference between the actual and the approximation, an absolute value. But for 4 decimal places, I need that error, that difference, to be smaller than, well, if I want 4 correct decimal places, that means I need a 0 here, a 0 here, a 0 here, and at least a 0 here, so that when I, again, do the subtraction, those digits are all the same. To be safe, I'm going to put 1 extra digit and then a 1 over here, so there's no rounding error that goes with it. But this is what I need to have happen. Now, just as a side note, we should prove this series converges using the integral test in order to be able to get a bound for the error using the integral test. But this is a P series. P is 6. It's greater than 1. We know it converges, and we prove that with the integral test. So I'm not going to go through all that work now because we've done the work to prove that. Now we're just doing this error-bound part. So basically what I'm trying to do here is figure out what value of n makes the error smaller than this 0.000001. Okay? So to do that, I'm going to take a look at, well, actually, let me put something in here. R sub n, we know, is less than or equal to the integral from n to infinity, and for this example here, 1 over x to the 6th with respect to x. Now, since I know this inequality is true, what I want to do is make this true. So I'm going to put point, let's see if I can squeeze it in here, like this. If I make the integral smaller than this quantity over here, then I know the error is going to be smaller than that quantity also. So that's the thought process that goes into this. Make the integral smaller than the value we want the error to be smaller than, because the error is smaller than the integral. Now, working this out, we ought to do all of our proper stuff. This is an improper integral, so let's get into this. Let's take the limit as t goes to infinity, integral from n to t, x to the negative 6th dx. And then get our limit. I'm going through this kind of quickly because we should know how to do this. We get negative 1 over 5x to the 5th. If that looks a little weird, just do the work it takes to understand it. You should be able to get that. And then we'll do our substitution. Get our limit as t approaches infinity. And then we get 1 over 5t to the 5th. Negative 1 over 5t to the 5th. And then with the subtraction and plugging it in, we're going to get a plus 1 over 5n to the 5th. And as t goes to infinity, this goes to 0, so this works out to be 1 over 5 times n to the 5th. And that's what we want to bound. That's find n so that's less than or equal to 0.0000, 5 zeros and a 1. I'm not going to spend, maybe I will. Okay, so multiply both sides by 5, and you're going to get this here. Take reciprocals and do a little bit of work. Flip the inequality here. This is 200,000 when you take the reciprocal. I've already done this ahead of time, so it's not me being really, really smart. It's just me being prepared. Then we got to take a fifth root, and when you get a fifth root, you get n is going to be greater than or equal to something that's about 11.4869. Now, since n is an integer, we're going to let n be equal to 12, and if n is equal to 12 for our nth partial sum, then our error is going to be bounded appropriately. So, actually, let's make that a 12. And so we're going to use the sum from n equals 1 to 12 of 1 over n to the 6th. If I run that through the calculator, I get, I had that a moment ago, so let me go back and redo it because I lost it. You get 1.0173424,118. Okay, just to give you way too many digits. This is our approximation right here. The actual answer, if I take what it is and write it as a decimal, it looks very, very similar. 3,4,0,6,198, and a bunch of other stuff. But notice we wanted 4 correct decimal places. Do we have 4 correct decimal places? We do. We actually have 5. We got good and lucky. We did put that extra 0 in there like we wanted just to make sure we got at least 4 correct decimal places, and we got it. Go study.